Hello, everyone, and welcome to AI4. Our next session will be led by SHWARTZ. Her title is Postdoctoral Researcher at the Allen Institute for Artificial Intelligence. Please join me in welcoming Vetted to the stage as she turns on her camera and starts sharing her screen. All right, it's all yours.
Thank you. Hi, everyone. I'm going to talk about recent breakthroughs and uphill battles in modern NLP. So I'll start by introducing myself. I'm a postdoc at AI2 and the University of Washington, and where I'm working on NLP, or more specifically on teaching machines common sense. Previously, I got my PhD from Bar-Ilan University, where I worked on lexical semantics. If you're outside the field, then you get your AI updates from popular media, then you might get the wrong idea that language is already solved, or moreover, that robots are dangerous. You would get that from reading headlines like Google's model understands language better than humans, or Facebook shut down the AI that invented its own language, and OpenAI don't want to release their models, claiming they're too dangerous to release. There's also funny examples from the end of last year where GPT-2, OpenAI's model, was used to predict the world in 2020, and unfortunately it was way off. It could have been a much nicer year. Inside the field, we're also looking at leaderboards that measure progress on various benchmarks. And they might also give some false picture of progress, because it seems like we are at human level on multiple complex tasks. In practice, if you ask people in industry, or if you just use NLP tools, you can see that some things work reasonably well. So a few of the common NLP tools that I use daily are autocomplete, grammar correction, search, and translation. And they work pretty well for English. Some of it is thanks to the encoder-decoder neural architecture. And this works as follows. So given an input sequence, like the English phrase, the white cat, this is being encoded using the encoder into a vector. And then this vector goes into a decoder that can output the tokens of the output sequence. So for example, here, if it was trained to translate from English to Spanish, it would output El Gato Blanco. But it's not only used for translation, it's also used for grammatical error correction, Gmail's auto response, image captioning, where the input sequence is an image instead of a text, and summarization, not so successfully yet, and many other tasks. So encoder-decoder models are efficient for tasks that require learning input-output mapping, and when they have enough training data. So let's talk about this enough training data. And I'm going to get a bit hand-wavy here, and I want to claim that humans generalize from a few examples. So for example, if you show a child a picture of a cat eating and you say the cat eats, then it's likely that the child is going to build some kind of an abstract cat representation. And then upon seeing similar cats doing other activities, they're going to be able to generalize and say the cat drinks or the cat sleeps. Or if there is a slightly different cat that's eating, they can still say the cat eats. This is not exactly the case for machine learning models, because if you only train them on a single example, they're gonna be pretty helpless in captioning different images. What you would need to do is show them multiple examples of many different cats in different angles, and then they would be able to say the cat eats. So models are data hungry. And as I've mentioned, these NLP tools that work in production, they generally work well for languages with enough training data. So specifically English and some other languages. One good example for that is Google Translate. Here's a figure from one of Google's papers, where they compare the amount of training data they have for the higher resource languages, which have around 2 billion instances, as opposed to the lower resource languages, which might have only tens of thousands instances. Instances for machine translation would be parallel texts. So the same text written in different languages in the source and the target language. And then the model is expected to learn mapping of phrases from the source language to phrases from the target language. So what happens when there's little training data? So this is a headline from 2 years ago, which by now has been fixed, but I think it's a good demonstration of that. So about 2 years ago, there was some news about Google Translate generating religious prophecies. Why does it happen? Let's look at an example first. This is an example I recorded 2 years ago. I set the input language, the source language to Igbo, which is a low resource language, which I don't speak. And I just inputted just a sequence of eyes and spaces, which I'm pretty sure is not a valid Igbo input. And then instead of the model saying, this input doesn't look correct, I don't know what to do with it, it just hallucinates some English sentence and it says, as it is written in the book of the law of Moses, which was in the wilderness, which was before the man who did the work of the kingdom of Israel, which I'm pretty sure is not what I wrote. So why does it happen? It happens because the Bible is the lowest common denominator of parallel data for machine translation. So even if Igbo and English don't have enough training data, the Bible is something that was translated across multiple languages. So it's probably going to contain the Bible. It might be the vast majority of the training data. So models fail to generalize to examples outside of their training domain. And maybe even worse, they don't even know when it's outside of their training domain. They can't just tell, I don't know what to do with this input. So the solution is that when it's possible, you don't train models from scratch, but instead you base them on an already pre-trained model and you apply transfer learning. And this is already happening in NLP over the last 2 years, following the vision community that started a few years earlier to train models based on a pre-trained model on ImageNet. Now we're doing the same in NLP using language models. If you heard some Muppet names, yeah, for some reason, all these models, except for the GPT series, they're all named after Sesame Street characters. So what are these language models? So they are trained in a self-supervised way on a large text corpus. And traditionally, language models are trained to predict the next word in the sequence. So for example, parrots are among the most intelligent birds, and the ability of some species to imitate human speech enhances their popularity so the model needs to predict pets. Starting about 2 years ago, Google developed BERT, which works in a masked language model objective, which is pretty similar, except that instead of predicting the last word, you can just mask out words in the across the sequence and just predict them. So this is what happens during pre-training, and typically what you would do is that you would take this pre-trained model and you would transfer it, fine-tune it for a specific task. So you do that by putting a classifier or some model on top of the representation and then feeding the specific task data. And then also when you compute the loss function, you backpropagate it to update the representation. So pre-trained models are trained once and then fine-tuned for each task successfully potentially with fewer training examples. That sounds good, but unfortunately, it's not like we just trained one language model and moved on to solve other NLP tasks. But instead, this has become sort of a competition between the large research groups. And if 2 years ago we were at 94 million parameters, then recently Google released a model with 600 billion, just shortly after OpenAI released GPT-3 that had 175 billion parameters. This is bad because it costs a lot of money to train. So for example, GPT-3 is estimated to have cost $12 million to train. And that makes it pretty impossible for most of the research groups, both in industry and in academia, to train competitive models. It's also unclear that this cost is justified. If you look at the performance on benchmarks, we've already exceeded human performance, and every new model just improves by a small margin. And finally, it's also bad for the environment. So last year, there was a paper that compared the estimated CO2 emissions from training common NLP models compared to familiar consumption. And this was even before the very big models, but it was already concerning. So models are huge. They are computationally expensive to train and use. And I would mention here that I am co-organizing a workshop in the end of the year called Sustain LP, in which we encourage building simple and efficient models for NLP. One of the other advantages of pre-trained language models is that they are dynamic, so they can compute the representation of a word given its context. So at the very basic level, words can have multiple meanings. So if I'm saying I'm using both the keyboard and the mouse, I mean the computer device sense of mouse, and the language model is going to assign some representation for mouse that reflects that. As opposed to if I'm saying the cat chased away the mouse, and then it's going to be more towards the animal sense. This is different from what it was only 2 years ago when we used static vectors. So we would just retrieve the single vector for a mouse that's in a strange way conflates the two senses. So finally, most of NLP research is context sensitive. This is thanks to the transformer architecture. It's not the first context sensitive architecture, but it's really efficient to use. But modeling context is hardly enough. There's so much more than context that we can understand from text, but these models are not really capturing. So for example, things like implicit meaning, if I say that I didn't eat anything since the morning, then it might mean that I'm hungry. Or broader context. So an utterance like no thanks doesn't mean a lot on its own, but in the context of a dialogue, it might mean something like I refuse to offer food. Non-literal meaning, like I could eat a horse, doesn't really mean that I'm going to eat a horse, it just means that I'm really hungry. Pragmatics, like do you have some food here, is just a polite way to ask for food. And finally, common background. So saying something like there is a new restaurant in the city, I'm likely referring to the city that we're in now, which I know is a strange thing to say in a virtual conference. And this gets even more complicated because in the US, depending on where you are, saying the city, you might mean a specific city, which is not necessarily the one you're in. But that changes depending on where you are. So that's really complicated, and no, these models don't actually capture these things. We also use language models to generate word knowledge or to capture, we consider them as capturing word knowledge, and it's far from accurate. So using Roberta, I can complete the sentence, a person has something, eyes. And then Roberta suggests numbers and colors, which are only partially correct. So for example, I don't have 3 red eyes. The same goes for legs. A person has 4 legs. And also, depending on the prompt, you can get different answers. So for example, a dog is usually and a dog is typically return different answers, like male aggressive, killed, small edible, and male. All pretty horrible answers, but they're also not consistent. So representations are inaccurate and they lack common sense. Some of it can be attributed to reporting bias, which means that the texts that we are training the models on, they don't capture a lot of word knowledge. There is a lot of word knowledge that they don't capture. And that happens because we tend to write more about the noteworthy things while ignoring the trivial things. So one good example is from the original reporting bias paper that shows that if you count the occurrences of actions in the corpus, you find that people tend to murder 4 times more than they breathe. One way forward is to learn not just from text, but also from additional modalities like images and videos. And here's an example for what you can learn from an image. So here you can see that being on the front row probably means sitting, might mean cross-legged, while being in the last row means standing. So does this lack of word knowledge even hurt the performance on downstream tasks? So I think it does. It's a bit hard to show it with the current tasks that we have. So I'm going to start with a real world example. These two tasks work significantly less well today because they require deeper understanding. And here's an example for a QA demo that someone shared with me recently, specifically one that answers questions about COVID. And I don't want to say something bad specifically about this demo. I just want to demonstrate that this is what QA systems look like today. So what I asked it here is, what is the risk of COVID-19 infection from touching public surfaces? And what I got as answers were answers for different questions like, what is the probability of transmission of the virus from Wuhan to other cities in China before the quarantine? Or what is the risk of getting infected by children? What is the ability to detect imported cases among high surveillance locations? And finally, there's one paragraph that is relevant, but it still doesn't answer my question. So that comes to demonstrate the difference between solving a task like QA versus solving a data set, which we do very well today. And the second part of solving a data set, I'm going to demonstrate with natural language inference. So in this task, the model gets 2 sentences and it needs to determine whether, given that the premise sentence is true, does it mean that the hypothesis sentence is also true? So for example, a street performer is doing his act for kids. Then a person performing for children on the street is true. A juggler entertaining a group of children on the street is neutral because it might be true, but we don't know for sure that the street performer is a juggler. And a magician performing for an audience in a nightclub is contradicting because assuming that they're discussing the same event, one happens in the street and the other one happens in a nightclub. So this is a very complex task. If you didn't understand it, then that's the reason. It requires knowledge about word meanings, understanding of syntax, ability to resolve references to entities, word knowledge, and common sense reasoning. Yet our models today achieve human performance on the leading data set. So why does it happen? Does it mean that they actually solve the task? Not so much. What happens is that our neural models are very good at detecting shallow patterns in the data that are not necessarily indicative of the actual task. So for example, here they can find things like a general word like outside appearing in the hypothesis is an indication of entailment, or longer hypotheses are usually neutral. And this one is my favorite. The existence of the word cat in the hypothesis means that it's contradicting because many of the premise sentences discuss dogs, and as you all know, cat is the opposite of dog. So models rely on shallow patterns that are not necessarily indicative of the task, and they fail to generalize. One of the reasons that it happens is because our data sets are somewhat artificial. This example data set was created by showing crowdsourcing workers the image captions and asking them to generate sentences for each one of the labels. And then naturally what happens when you perform a task that when you're paid per task, then you naturally develop the best strategy to answer it with the lowest cognitive load. And then you come up with ideas like replacing dogs by cats or adding negation, which are very easy for the model to pick up on. Another problem is that it's hard to tell whether a model learned valid or spurious patterns for some tasks, and that's because models are uninterpretable, neural models in general. And this leads me to the final point, which is that AI models, they also learn bad things from us. So here are multiple examples from news over the last few years. For example, Microsoft chatbot became racist, and some gender bias in various applications and racial bias. So overall, models perpetuate social biases. And I'm going to focus on the example of Amazon's CV filtering algorithm that was discriminating against women. And I'm going to try to answer the question of why did it happen. So many things could go wrong, but some of these are, first of all, bias supervision. So when you train such a model, you usually train it on the training data would be previous decisions made by people. And people are biased. So it may as well be that the person that made the previous decisions for some reason thought that men are better qualified for some job than women. And it could also be that there's just not enough women in the training data. The second thing is biased representation. So it has been shown that word representations capture gender bias and also racial bias. So for example, that men is more semantically similar to programmer than woman, which is more semantically similar to homemaker. And finally, since our models are not interpretable, it's very hard to even find these biases unless you specifically probe the model by, for example, showing it two identical CVs that are only different in the, one of them has the female first name and the other one has a male first name. So to sum up, here's the checklist of what we want our models to do. We want them to seamlessly learn input-output mappings. We don't want to train them from scratch every time, and we want them to be context sensitive. This is all pretty much there, but we also want to use fewer training examples. We want them to generalize outside their training domain, to be smaller, to capture accurate common sense knowledge, to solve the task instead of learning data-specific shortcuts, to be interpretable, and not to perpetuate social biases. And so we still have a lot of work to do. Thank you.
Thank you so much for that insightful presentation. I learned a lot, and I know that the audience did as well. So a huge virtual round of applause for you, BERT. Thank you again. So if you're looking for your next session on the program, you can go ahead and check out the program page to find where you're going next. Also take some time to do some networking sessions and get involved with your fellow attendees. Thank you so much, and we'll see you around.